All right, welcome back. So, second talk will be by Dr. Sunjin Choi from IPMU, Japan. He'll talk about AdS black holes from quantum field theory.
Thank you very much for the introduction, and I will also thank giving me an opportunity to talk here. Today I'll talk about AdS black holes from quantum field theory based on basically summarizing some of my works. So my talk will be divided into two parts. In the first part, I will talk about the index, illustrating how can we extract the black hole entropy from the index, basically what was reviewed by Alejandro in the former talk. So in the first half, I will speed up a bit, and on the second part, I will focus on the individual black hole microstate in the language of supercharged cohomologies, and using this, I will try to convince you that it can actually predict new supersymmetric black holes in AdS5, which was recently constructed also in gravity side. So let me first start with a very brief introduction. So as you all know, black holes are fundamental object in gravity described by a smooth geometry of general relativity like event horizon. And at the same time, they encapsulate high energy states in discrete spectrum of quantum gravity. And because of that, black hole serves as a theoretical probe to understand important and mysterious properties of quantum gravity. So what are these mysterious properties? While the graviton states are well understood, the black hole microstates are a bit special compared to them, while they are both the fundamental degrees of freedom of quantum gravity. So you can ask, how does emergent geometric description arise from such microstates? How can we understand holographic property arising from them? Can we understand some maximally chaotic behavior of them? Can we understand or resolve the black hole information paradox studying those microstates? I cannot answer to all of these questions today, of course, but I hope that you will get some lessons toward this direction from my talk. So one ideal way to study this kind of questions about black holes is to utilize the AdS CFT correspondence. Basically, we're going to study quantum gravity in a covariant box obeying the equivalence principle, which is actually the antidigital space-time. And it has been known that gravity in antidigital space-time is holographically described by component field theory on the boundary. And one of the famous and today's example is the type 2B string theory on AdS, on asymptotically AdS5 times S5, dual to four-dimensional n equals 4 supersymmetric Yang-Mills theory. And in this setup, the semi-classical gravity in the bulk is emergent when CFT dual has large degrees of freedom and also strongly coupled. So how does the black hole can be seen from the CFT side? So it is also well known from several years ago. So in the gravity side, we know there is a Hawking phase transition in AdS. At low temperature, the dominant thermodynamic phase is governed by thermal gas of gravitons propagating inside AdS. However, if you increase the temperature, they collapses to make a special black hole in the bulk. And the dual picture of this phase transition is known as the confinement-deconfinement transition on the boundary sphere. So at the low temperature phase, you will see the confined hadrons, but at enough high temperature compared to the scale of the sphere, you will see the individual deconfined quark-gluon plasma, and this phase is thought to be dual to the black holes in the bulk. So what we want to see is to find the deconfined quark-gluon plasma phase from the field theory side. So this is just a brief introduction before going into the details. So if you have any questions, please interrupt me anytime. So today, we'll study 2B string theory on AdS5 times S5 holographically from 4D n equals 4 super Yang-Mills. And in particular, I will focus on so-called 16 BPS operators, which is annihilated by one Weingart supercharge and one conformal supercharge, which is actually the Hermitian conjugate of our chosen supercharge in radially quantized setup. We will put our theory on the sphere after radial quantization. And this is the superconformal algebra satisfied by these two supercharges. And here H is the scaling dimension, Ri's are Cartan charges of SO6 are symmetry, and Ji's are Cartan charges of SO4 angular momenta. And the 16 BPS operators, which are annihilated by both of these charges, satisfy this BPS relation. Scaling dimension equals to sum of R charges and angular momenta. And in the free theory side, you can easily read off which kind of letters, which kind of fields satisfy this BPS relation. We have 3 scalars, 3 Carolinos, 2 Gauginos, the anti-self-dual component of the field strength, and you can add arbitrary number of holomorphic derivative on them. So combining these letters, you can construct general gauge invariant local BPS operator in the free theory side. So in the first half of my talk, I want to count the number of these BPS operators. Actually, I want to do it in the strong coupling limit to study the gravity side. So how can we compute or count the number of these operators? Is to utilize the so-called superconformal index. This is nothing but the Witten index type thermal partition function on 3 sphere given as this. And here we introduce the chemical potentials for the R symmetry and angular momenta, which satisfy this constraint. So these 5 chemical if these 5 chemical potentials satisfy this constraint, this exponent is commute with our chosen supercharge. So since we have -1 to the F, this will be protected under any continuous deformation as usual. So it can be computed exactly at recoupling to study strong coupling dynamics, which we want to study, where gravity emerges. But one issue about this index is that because of the formulation, this counts the BPS operator with -1 to the F. So you may worry about the Bose-Fermi cancellation. So maybe if the Bose-Fermi cancellation is so severely happens, so then maybe this index cannot capture the black hole entropy. And that was a long-standing problem. But today I wanna convince you that that is not the case, and actually we can extract the Lagrangian-Hawking entropy of the black holes from this index. So in order to see that, let us start from a very basic approach. So we first unrefine all the chemical potentials. So we have only one viscosity X right here. So our index can be written as this, which can be expanded in terms of X, like this. And this index can be computed using the unitary matrix integral. And the derivation of this matrix integral is quite simple. So this vector is called as the single particle partition function, basically counting the BPS operator, which contains only one field, which I showed you here. So this will give you this vector. And then since you want to compute all the multi-particle operators, multi-trace operators, you should exponentiate it to get the multi-particle partition function or multi-particle index. And then you want to only count the gauge invariant operator, right? So you want to project into the gauge singlets, and that can be done using the Hameser integral like this. After this contour integration, you'll get only the number of gauge invariant BPS operators. So one approach one can do is to first expand this in X and compute residues of this integral using computer up to reasonably high orders in X and reasonably large N square, and see whether they at least approximately saturate the back-engine Hawking entropy of the black holes. And you can see actually it does. So this is U5, U6. You may think that 5 is too small, but 5 square is 25, so it's quite a big. So this dots indicates the log of omega j with absolute value. And this black line, solid line, is the black hole entropy, which you naively insert the n square as 25 or 36. So at reasonably large charge, you can see that actually the index well saturate the black hole entropy. So the index really do exponentially grow, saturating the black hole entropy. One more, but there is more than that. So here you can see the red dots and blue dots. So blue dot indicates when the degeneracy is positive, and red dot is when the degeneracy is negative, meaning that boson dominates and fermion dominates. So you can see the index not only just grow rapidly, but also they exhibit a rapid sign oscillation between the envelope function given by the black hole entropy. This is a different behavior of the index compared to the normal thermal partition function. So in thermal partition function, you'll have just exponential growth, but since we are studying the index, you have not only the exponential growth, but also rapid sign oscillation. And the question will be, how can you account for this kind of sign oscillating exponential growth from the saddle point approximation? Actually, this agrees to the graviton degeneracies, and lower charges you should better match it with graviton, and it matches very well. And if you go to large charges, it matches below the line. Yeah, that's also true. Yeah. So can you account for this sign oscillating exponential growth from the saddle point approximation? How can you do that? We did not learn this from our statistical mechanics. So recall that Legendre transformation is the saddle point approximation of the inverse Laplace transformation at large J. So this is the inverse Laplace transformation extracting the degeneracy, and at large charge, we want to do the saddle point approximation, which is the Legendre transformation. And this is what we want to extremize in terms of omega. And our claim is that for this sign oscillating growth, we should find the complex saddle points at real charge, meaning that in use of thermal partition function, after the Legendre transformation, you will get real temperature. But in the index, we are claiming that we should find some complex, let's say complex temperature, or more precisely complex chemical potentials. And naively, this leads to complex entropy, and you will say, what is this? But that's not the end of the story. So basically, the unitarity of our quantum field theory guarantees the existence of complex conjugate saddle points for any complex saddle, meaning that we should add to equally dominant contribution from the conjugate pairs, like this. And this will give you exponentially growing envelope function times oscillating factor between +1 and -1 by this cosine function. So full entropy is given by this, and the first term will give the macroscopic degeneracy at large charge J, which accounts for the back-engine Hawking entropy. And the second term is, while it is typically subleading, but the main point is that this will govern both the signs and also subleading oscillation of entropy near the black hole entropy. So this is new plot drawing this sign oscillating degeneracy. And you can see that actually the signs and the subleading oscillation of the degeneracy and this cosine function very well match at large charge J. Yeah.
So one feature is that so the points nevertheless remain close to the black hole. There are no points that go all the way down. So they understand why.
Sorry.
So in principle, cosine should allow me for open.
You are wondering why it does not go to, let's say, 0 or something like that. Well, that's a great question. It's probably, how can I say? Well, actually, honestly speaking, we do not know why does it happen. So basically, if you increase the charges, what we observe is that the degeneracy is oscillating just like this entropy. But as you say, we don't have really absolute zero at certain charges. And this might be some hint for the black hole entropy at how can I say, in one run expansion or something like that. So you will not have zero entropy at any charges. Well, this is the exact result from the index. There is no error. No, cell point approximation is this line. And that's our exact result. Yeah. Sure, but sure. That's that will appear about end of my talk. And so at this point, I only find all the Figastis, and it is, well, I think it is generally believed or partially shown that in this unrefined sector, the black hole setting point is always dominant, and at least at large charge. Yeah. Yeah. It also has one-to-one corrections. Yeah, that's true. So if you want to see whether there will be some really zero, then you should also consider some all one-to-one corrections precisely. So any questions at this? Okay. So what we learned from this numerical exercise is that in order to extract macroscopic degeneracy from the indices, which rapidly sign oscillate, you are forced to find the complex saddle points. And there are always complex conjugate saddle points, and adding them will give you macroscopic sign oscillating degeneracy. So one convenient way to study complex saddle point from the index is in this setup. So basically, you absorb -1 to the f using the reparameterization of this, let's say, one chemical potentials and impose the constraint like this. Okay. So now the linear combination is 2 pi I. This exponent is does anti-commute with the supercharge. So this will define the index. And the unitary matrix integral is given as this after unrefining all the chemical potentials. So we want to find the cell point of this integrand at generate complex chemical potentials. Yeah. Sure. Yeah. No. So index cannot see any constraint. No, I mean, this J is actually the linear combination of J and Q. So this entropy does not know whether the charges satisfy the nonlinear constraint or not. Well, yeah, that is also true, but well, so yeah, when you say the imaginary part of S is zero is a bit weird notion because it is the nonlinear constraint is only derived at n square order, right? But this is not n square order. This is subleading oscillation near the entropy, so yeah, it's a bit different. So we want to find a saddle point of this integrand. And one easy way to find the saddle point of this integrand is to focus on the cardinal limit, where this angular momentum chemical potentials become very, very small. And you will find that the integrand is actually greatly simplified as this. In this limit, all the charges become very large. So this is analogous to the high temperature limit of the thermal partition function on the BPS surface. So if we find some large saddle point in this limit, the saddle point will be dual to large black holes, very, very large black holes in AdS. And this Li3 function can be combined into the Baronian polynomial as user, and you will find that because of because you only have the adjoint representation because of the symmetry, you'll find that actually the maximally deconfining saddle point dominate this integrand, where all the gauge holonom is equal. And actually, this result is expected because in the high temperature limit, you may think that all the matrix degrees of freedom will be liberated. So you don't want to put any mass from the gauge fugacities. So if you set all them to be equal, then the mass parameter giving to all the n square matrix of degrees freedom becomes zero, so they are all liberated. And then you may ask that what happens if we decrease a temperature of B? Then the natural guess is that this saddle point will be spread in such a way. And that is true. And one way to study that is to reorganize the integrand into some kind of special function known as the elliptic gamma function. And one nice property of the elliptic gamma function is they satisfy some SL3Z modular properties. So this is very much similar to the SL2Z modular property of the Jacobi zeta function. And you can use some S transformation of this elliptic gamma function, and you will find that because of the SL3Z modular property, well, just like the SL2Z modular property of the Jacobi zeta function, the doubly periodic configuration like this parallelogram distribution can serve as the saddle point of this integrand given by the elliptic gamma function. So this is the saddle point of our problem. And if you insert this saddle point to get the on-shell action or the free energy, you will get this expression. And it has been known that even before we computed the index, if we extremize this log z, or more precisely, if you perform the Legendre transformation, this will give you the correct, precise Bekenstein-Hawking entropy of the BPS black holes in AdS5 times S5. Thus, we successfully statistically accounted for their microstates. Oh, that is a very great question, which I don't have a clear answer. So in 2D, you have torus and you have this SL2Z modular properties. And the index is defined on S3 times S1, and this elliptic gamma function sees some symmetries of S3 times S1, and that is realized as some S3 is modular. Yeah. Yeah. Actually, this is properties of the integrand, not the total, not the resulting index. So it is not well understood. Okay, so I want to move on to the next part. So before going to the next part, any questions in this index analysis, studying the Bekenstein Hawking entropy? Okay, now let's move on. So we have a nice formula. We capture the Bekenstein Hawking entropy from the index, and using this, you can do very many interesting things. For example, you can use this analysis to the giant graviton expansion in the gravity side to capture which is thought to be the string theory partition function on AdS 5 times S5, then you'll see that you can interpret the black hole microstates as actually the bound states of the brains, or you can you may ask whether can we study the index in different space-time dimensions, and then you will find some intriguing properties that, let's say in 3D, you will find the monopole operators take very important role to realize the n to the 3 half degrees of freedom. And in 5D, you will find instantaneous returns take the important role realizing n to the 5/2. So there are many interesting directions, but today I want to focus on the individual black hole microstate inside the horizon, which is counted by the index. So I want to convince you today that, let's say in SU2, like SU2 gauge theory, the graviton microstates look like this, while the black hole microstates look like this. So yeah, I will explain what this means. But anyway, when you have this kind of operators, then what can you learn from it? I will explain or illustrate that from this operator, we can predict, we predicted new supersymmetric black holes in the gravity side in AdS, that is the hairy black holes, which were constructed recently. So let us start. So in order to study this individual microstate inside the horizon, now we want to focus on finite N gauge theory. Well, it'll be better to study large N gauge theory, but it is technically difficult, so I would like to start from finite N. So, which means that Newton constant in the gravity dual is finite. However, I will show you that even in such a theory, we can distinguish between graviton and black hole states. And these finite and black hole states can be thought of as some, let's say, quantum black holes in AdS. And the most interesting thing is that they exhibit certain properties of semi-classical black holes. So we can study the behavior of semi-classical black holes from the finite N gauge theory operator spectrum. So how can you study this? This is actually the slide I already shown you, but let me just explain it again. So in the free theory, the BPS operators can be made by combining these free BPS letters, 3 scalars, 3 Carolinos, 2 gauginos, field strengths. But I want to do more than that. I want to go to the one loop order. And it has been known that this QQ dagger anticommutator receives quantum fraction at one loop level, meaning that lots of BPS operators in the free theory acquire non-zero anomalous dimension at one loop level, and they become non-BPS. So our conjecture is that there will be no further correction at higher loop or by any non-perturbative means. And recently, by Qiming here and his colleague, this vanishing perturbative corrections in 16 BPS spectrum is partially proved. So I will just assume that this conjecture is true and study the wall loop BPS operator and utilize them to study the strong coupling spectrum. So now at one loop, 16 BPS operators are harmonic forms of QQ-dagger anticommutator. And since these QQ, supercharged Q or Q-dagger are nilpotent operator, using the standard Hodge theory, you can one-to-one map these harmonic forms to the Q cohomology classes, whose non-trivial elements are Q closed, but not Q exact, meaning that it cannot be written as Q action on some operator, but it is still vanish when you act Q on them. And so in this cohomology language, one advantage is that you don't need to care about Q-dagger, you only care about Q. And because of that, you can read off the Q action from the classical field theory on the free VPS letters. And now the Q action becomes like this. So there is scalars and gauginess also vanishes. But now at finite coupling, this Carolino field strength and gauge covariant derivative do transform under the Q action. And our goal is to construct representatives of cohomology classes using these relations, which are not dual to the gravitons in the bulk. Any question about this setup? Okay, so then I should explain what is the operator dual to the graviton and what is the rest. So in the gravity side, the BPS graviton state, today in my talk, when I say graviton, it actually means all the perturbative particle states, not only the graviton, scalars, photons, fermions. So anyway, these perturbative particle graviton states can be defined at zero neutral constant. And one can find local BPS operators in super young mills dual to such states at n equals infinity, which carries finite energy. And you can easily show that they persist to exist at arbitrary finite n. They are BPS operators at any n. You first constructed n equals infinity, and you will find that they are BPS at any finite n. So these are called as graviton cohomologies. And so from the definition, you'll see that the number of them does not scale as n. However, we know that there are black holes in the bulk carrying e to the 1 over g number of states. So correspondingly, there should be to the n square number of dual BPS operators in n equals for super young mills, which carry n square energy. So compared to the definition of these graviton cohomologies, you will find that there should be extra BPS operators at finite n, which are only BPS at certain n due to the trace relation, meaning that due to the finite size effect of the matrix. And our claim is that this kind of operator, the number of this kind of operator will scale as e to the n square, which are responsible for the Bekenstein-Hawking entropy of the black holes. So we will call it as black hole cohomologies. And actually, I borrow the cartoon from Qiming's paper. So this is the behavior of the graviton operators. This delta is the anomalous dimensions in terms of n. You'll find that they always vanishes. But if you find some, let's say, black hole operators, their anomalous dimensions will be zero only at certain n, but becomes non-zero at the other ends. So because of this behavior, we'll also call this graviton cohomology as monotone, and this black hole cohomology as fortuitous operators or cohomologies. No, it's 16 BPS. Today I will only talk about 16 BPS. I, actually, I will show the example of what I mean by gravitas. So we will start from the single trace cohomology since Q does not change the trace number. And the superconformal primaries is nothing but the symmetric trace of scalars given as this. Actually, this is the half BPS. But then we now act the fermionic generators which commute with our chosen supercharges to get the 16 BPS superconformal descendants of them. And these can be arranged into the short multiplet of this commutant of the full superconformal group, which commutes with our chosen supercharge, and they are called as N multiplet. And it has been shown that actually this multiplet is absolutely protected, really. So, for example, in S2 multiplet, the conformal primaries are given as this. You have traced by phi, and also traced by lambda, and gauging by linear, also scalar times Carolino, scalar times field strength, and so on. And you can multiply the above cohomologies, and that will give you multi-trace cohomologies. And these single trace and multi-trace cohomologies correspond to the single and multi-particle graviton states in AdS5. Okay, these are the graviton cohomologies. But if we go to the finite n, still the formal construction gives cohomologies at arbitrary n, as I explained. They are all BPS. But what happens is that they are not all linearly independent. You construct some redundant basis of operators. The number of independent cohomologies reduces due to the trace relations when the number of fields become larger than n. For example, in SU2 theory, you can think trace x square, y square, or trace xy, something like that. And if you subtract these two multi-trace operators, they become Q-exact, meaning that actually they are the same operator. So the number of independent operator reduces at finite n, and this is actually well understood also from the gravity side, known as the stringy exclusion principle. In AdS5 gravity, the gravitons, if you excite energy more than n, they are polarized into the disrebrain giant gravitons, and this reduces the allowed number of states. So all these graviton cohomologies, even at finite n, are well understood. So, but as I explained, there should be some other types of operators which is responsible for the black hole degeneracy, and our goal is to construct such operators. Any questions? If not, I will move on to really the construction of black hole operator. Yeah. Okay. Constructing these black hole operators in full super Yang-Mills theory is a bit technically difficult. So I want to truncate our problem into the subsector of the n equals 4 super Yang-Mills with no derivative. Without derivative, our life becomes much easier. So if you do not excite any derivative, simultaneously, you should not excite any gauginos because the Q action on the derivatives will give you gaugino. So you should only excite scalars, Carolinos, and field strengths, and they are the fields which are excited in the BMN matrix model. So I will call this sector as BMN subsector, and these are the Q action on them. And you can compute the index over these BMN cohomologies like this. And one nice thing is that since now you have no derivatives, the integrand is, inside this quadratic exponential is the finite polynomial, so you can compute the index exactly, not order by order. You can compute the index exactly in this subsector. And you can show that even in this subsector, the index exhibits n-square entropy at large n, so there is really a black hole even in this subsector. So, and also sometimes I will unify the fugacities as this for the illustration purposes. So you can compute this index in the BMN subsector exactly. And the next thing, what we have done is to count the number of independent gravitons at finite n. So you may think this is just a straightforward, easy problem, but it turns out that it is straightforward but technically difficult problem, okay? So I will just skip this technical part, but anyway, using some difficult mathematical languages, you can count the number of the independent graviton using graviton basis. So in SU2 theory, we could find the graviton index like this. This is a closed form expression, precise expression. However, for let's say SU3 and SU4, we could not get the full answer, but some answer until certain orders. Anyway, we compute this graviton index. So next, what we want to do is to subtract this from the full index, which will give you the index over BMN black hole operators. Like this, quite a simple form. And if you unrefine all the index, you will see that actually the non-trivial black hole operator first appears at T224, which was originally reported by Chiming and his colleague. Okay, so we have three factors, but actually the second factor is trivial. It's just the fact coming from the superconformal descendant, so it is trivial. And also third factor can be understood well. This is nothing but the multiplication of the certain graviton triplet on top of new operators. So actually the first factor is genuinely new part, which we should explain. And after the unrefined, you'll find this series, which implies that you need to find unique fermionic cohomologies, unique fermionic black hole cohomologies at charge level 24 plus 12n. And for the simplicity, now I will use the vector notation for the SU2 adjoint fields. And after some computation, you can find this. So this is the black hole operator in SU2 theory. If you wish, you can say that this is, let's say, most quantum black holes because you find it the smallest n and it carries smallest charges. So anyway, this is the black hole operator we found. It carries scaling dimension 19/2. And you can show that this V is nothing but the graviton. But then you multiply some fermion triplet and contract all the indices and they become non-trivial black hole operators. And then you will find all the tower of black hole operators. You don't have to know the details, but one interesting feature of these operators is that if you multiply any of these operators, they become zero by Fermi statistics. This is one interesting properties of the black hole operators we found in SU2 theory. So we have these operators. You can try to see several interesting properties of black holes from these operators, like giant graviton or Fermi surface interpretation of this operator, or some, let's say, higher spin, or you may imagine some emergent higher spin tower protected by some symmetries and so on. But today I want to focus on some semi-classical black hole properties of these black hole operators. Mainly, I want to predict new supersymmetric black holes in AdS, studying the properties of this operator. In order to do that, one way is to consider some finite energy excitation outside the horizon and see whether it is absorbed by the black holes or can we have some stable configuration outside the event horizon. And in the CFT language, this can be studied by multiplication of the graviton operators on top of the black hole operators. So these black hole operators can be thought of as nothing but the black hole creation operator in the bulk. So you first create the black holes, and on top of that, you also excite the graviton outside the event horizon. And one interesting fact is that if you multiply these conformal primary gravitons on top of the black hole operators, they become all QZ. meaning that they disappear from the 16 bps spectrum, so they don't exist. So this is reminiscent of black hole no hair theorem. BPS black hole doesn't allow this kind of hair, this kind of BPS graviton hair. And also, so from now on, I'll only focus on these scalar gravitons. So follow this circle. So if you can add one derivative on them, then you will also find that they also vanish from the 16 bps spectrum. You may ask, what if x 2 or more than that? Then interestingly, you will find them in 16 bps spectrum. So if you multiply conformal primaries or some conformal descendant with small angular momentum on top of the black hole operator, they disappear from the 16 bps spectrum. But if you consider some conformal descendant with large spins, then they are still there in the BPS spectrum. Then these may imply the existence of hairy BPS black holes in AdS5 with large angular momentum here. So can we construct that? So simplest BPS black holes in AdS5, the Grotowski-Rel black hole are parameterized by one parameter Q. And this is the cartoon of that. So this is the BPS line at fixed angular momenta, with energy and charges are here. And this yellow line is the line for the extreme of black holes. And you can see that they only meet at certain point. So BPS black hole only exists codimension one surface on the full BPS surface. And this is known as the nonlinear charge constraint of the BPS black holes. And you may ask that, why can't we find the black hole solution, BPS black hole solutions, on the outside of the charge constraint? Why there are no BPS black holes in this region? And why there are these gap between the BPS surface and the extreme of black holes? And I want to show that we can actually fill this gap and find a new black hole solution on this full BPS surface. So as a toy example, let us consider the bosonic proparticle dual to Chiral primary in the black hole background. And you can find that easily that rotating BPS solution outside the horizon only when its angular momentum exceeds some charge combination of its charge and black hole parameter, and which can be intuitively understood. If you have very small angular momentum, it will be swallowed by the black holes. But if it has large enough angular momentum, the centrifugal force can be balanced with the gravitational attraction. And you can also promote it to the wave picture. So you solve the BPS equation outside the event horizon, and this is the solution. Looks a bit complicated, but actually this angle-dependent part is nothing but the usual derivative factor acting on the conformal primaries. So you need to see just this radial part. And you will find that at the horizon, the solution remains finite only for the most satisfying, when this angular momentum quantum number exceed certain combination of the black hole parameter and the charge of the scalar field. So there are only the modes with large angular momenta are allowed to superpose with black holes with small bang reaction. And actually you can consider some thermal ensemble of this allowed hair outside the event horizon. And this is what we call the gray galaxies in our papers. So we have black hole in the center, and we have some hair with larger angular momentum, which is white. So that is why we call it as gray galaxies. Yeah. In the problem, we do not consider any bang reaction of this. Sorry? Just solve the BPS equation on top of the black hole background, and we just neglect the effect of this to the metric. Yeah, in full nonlinear level, we don't solve, but at the first perturbative level, we find the BPS solution. That is what I'm saying. Sorry? boundary conditions and UV. Yes. No, the bar boundary is just vacuum AdS 5 as usual. So this kind of behavior also can intuitively understood. So when you consider some conformal primary, it prefers to be at central region of the AdS, which is hidden inside the event horizon. That will be more likely swallowed by the black holes, and then we have more strongly to have some kind of non-BPS black holes, but filled with higher M most rotate outside the horizon. So can be proposed with small bang reaction. This is the mechanism how we construct the BPS gray galaxies. And so we found why conformal primary cannot grasp the black holes in the superposition picture, and we found why particles with large angular momentum can provide pairs of BPS black holes, which is qualitatively accordance with the CFT operator spectrum in SU2 theory we found. And we have more qualitative evidence of this solution. So as I said, we only solve the BPS equation at the first quadratic level. So you may wonder that this solution exists at full nonlinear level in the BPS surface. Of course, the best way is to construct the full nonlinear construction. And what is it? Yeah. Well, it just means that with large angular momentum here, you can superpose it with small bang reaction. That's how we construct our hairy black holes. But if you consider some conformal primary things, then they will be swallowed and they become dynamically unstable to construct some other complicated configurations. Zero? What do you mean by zero? No, when I say the small bang reaction, it compared to the 1 over G scale. I mean, 1 over G to the some power, I forgot. Yeah, so you can systematically compute the order of bang reaction. And we show that it is negligible. Well, 1 over G is large. G times some positive power of G. Yeah, the bang reaction is suppressed by some positive power of G. Yeah, okay. So we can also compute the index numerically at some finite n. So I showed you that if you unrefine all the chemical potentials, the index saturates the entropy of the known BPS black holes. But if we refine one, let's say angular momentum chemical potential, you can see that at large angular momenta, the index is very much different from the black hole entropy, given as this. Rather, at large angular momenta, I mean large difference of the angular momenta, you will see that it is qualitatively more similar to the entropy of the gray galaxies, which we draw in the yellow line. So yeah, it is more likely that there is some gray galaxies in the gravity side. So then you may ask whether there are some black holes with charged hair, not this angular momentum hair. Then you can find some signals in SU3 theories because you can find some Kaluza-Klein tower with increasing number of charges. So this is the tower, and you can, and this implies that you can find some hairy black holes with large charged hair, and we constructed it as dual-dressed black holes, basically black hole surrounded by large dual giant graviton or large D3 brains. No, this is different one. Dual giant, the D3 brains wrapping the black hole horizon. Large D3 brains wrapping the black hole horizon. Not on the boundary. Yeah. Is at square root of 1 over G. The radius will be proportional to the square root of 1 over G. And its bang reaction is also suppressed by some positive power of G, which I forgot, sorry. But anyway, you can systematically compute the power, estimate how it bang reacts to the geometry. So, well, let me skip this part. This is another black hole operator, which looks horrible. And so this is the summary we found in the black hole cohomologies. We studied the 16 BPS operators. Some of them are graviton, and some of them are black holes. And actually, in the black hole operators, we interpreted some of them as 4 black holes and some of them as the dressed black holes, dressed by the large conformal descendants of graviton or large dual giant, which we constructed in the gravity side, at least perturbatively, as the gray galaxies and the dual dressed black holes. So let me summarize the second part. So we studied cohomologies of local BPS operators in n equals 4 by Yang-Mills, and I showed that we can distinguish the cohomologies for graviton and the rest. And for the rest black hole operators, we constructed an infinite family in SU2 theories, and I showed the partial no-hail behavior. So conformal primary gravitons cannot rest, while conformal descendant can rest these operators, and we provide a gravity interpretation of this phenomena, constructing hairy BPS black holes, what we call gray galaxies. And also in SU3 theory, we additionally found some tower of states, which we interpret as dual to the BPS dual dressed black holes surrounded by large D3 brains on top of these black holes. And there are still many interesting future directions, higher N or less supersymmetric series, or since we have definite operator representation, you may want to compute some kind of correlation function to study operator complexity or quantum chaos. Or now we propose some hairy black hole solutions in the gravity side. You may want to find the large and saddle point dual in the field theory side. Or in the gravity side, you may want to construct some nonlinear construction of this solution. And actually, dual dressed black holes may be, I'm not sure, may possible because we have large dual giant gravitons far from the horizon. And you know that the full bang reaction of this dual giant will give you the LLM geometries. And so here the central region, we have 16 BPS Kutosi-Rel black holes, and very far region, we have half BPS LLM geometries. And I'm wondering if we can find some nonlinear, we can find some connection between these two geometries to construct nonlinearly this dual dressed black hole solution. And you may ask whether, let's say, genuinely new geometries are there, let's say, what we have in the flat space, multi-center black holes or black holes, and so on. That will be also very interesting. So with that, I'll finish my talk. Thank you for listening.
Thinking that you have
Charge plane means this BPS group?
yeah.
Yeah. Numerics means you mean index or what? Cohomology, we found a bunch of these hairy black hole cohomology. Whole BPS plane. Yeah, right. Right. Yes, I mean, for, yeah, well, whole means you mean after the infinite charges, we cannot construct arbitrarily large hairy black hole operators, but as far as our technique allows me to construct cohomologies, we found on top of this operator, we found any cohomologies with arbitrarily large angular momentum and arbitrarily large charges until certain orders because our technique go off. Yeah, we found this. We covered this BPS surface until certain range, because we cannot go to very high. Well, if you fit the BPS surface, it will fill the BPS surface. Yeah. Yeah, I mean, until certain order, until certain charges. For each charge we can find, I mean, this operator plus one electric charge, two electric charge, three electric charge we constructed. Yeah. Yeah, I mean, changing the R charges, we found the operator. Cancellation, no. Why should it cancel? No. No. They have all the same from statistics. Why not? I mean, this is the operator. With me.
It's other district part. You're in one or one. Is that right?
Yeah, one AdS charges. Yeah. Yeah. Now I understand what you're saying about. Yeah, if you fill all the BPS surface, then you might wonder if they cancel each other. Yeah, you're right. But yeah, we don't find this nearest neighbor of both which can cancel each other boson fermion. We only found the fermionic thing, so maybe two jump. Yeah, well, is the prediction in large and I mean.
Yeah, I have a slightly different question. So in the question you want to type of the also how in this case a large class of microstates are also analyzed. Microstates.
Right.
You choose a microstate.
Yeah.
And try to create that.
Well, actually, I haven't studied this fortuitous cohomologies in D1, D5 CRT. I know that Shiming has been. And yeah, I did not. I did not do anything to the D1, D5 CRT. Yeah. So,
This question is the state.
you also some some kind of microstate geometry, and I don't think that is possible. Yeah, I mean, well, I'm now trying to consider to study. I'm trying to study this 3-point or 4-point function, but I haven't done it. I haven't got any result yet. Yeah. Yeah. Large. Yeah. No, this is for the gray galaxy. So you have large. This is for the gray galaxy. You have graviton gas outside. Yeah. Yeah.
This guy.
Yeah. They don't give it. Yeah. I mean, you should consider some equilibrium between the large angular momentum here and the black holes, and then you should distribute charges appropriately between the black holes and the angular momentum here, and then you'll find this kind of entropy behavior basically from this core black hole. Yeah. No, this is a while loop. These are all while loop operate. I mean, I changed my language to while loop from while loop operators to the BPS cohomologies. But anyway, this is all about the while loop operators. Yeah, it is very much different from the free theory. So I'm studying the operators which remains to be BPS even at while loop order. Yeah. What's the entropy? I mean, you mean from our fortuitous, let's say this kind of analysis? Well, we are at very small n, so we don't have e to the n square entropy, unfortunately. If you really account for the Beckenstein Hawking entropy from this kind of fortuitous cohomology business, then you should construct this at fairly large n. Yeah. That is some computation at large n. Yeah. Well, where is this? Well, n square is 100 is large. Yeah. Yeah, and no qualitative difference. Yeah. It is a bit changed, but anyway, like this, like this. So these are not the conformal descendant of these operators. Yeah. Distributing the charges between the hair and black. Yeah. So yeah, that's true, but yeah. What? At this region, you don't have black holes and you have great galaxies and they dominate. Actually, we have some kind.